Lecture problem 6. A mass m starts at rest on a frictionless track a height h above the floor. It slides down to the level of the floor where it encounters a loop of radius r. What is the height h if the mass just barely makes it around the loop without losing contact with the track? Before deciding about the best tools that can be used to solve this question, let's set the free body diagram first and discuss it. The object at all times is under two forces only: the weight mg, which acts straight down, and the normal force, which is perpendicular to the surface of contact. Notice that the mass is under a single non-conservative force, which is the normal force. And since the normal force makes a perpendicular angle with the displacement, therefore the work done by the normal force is equal to 0. As a result, the work done by the non-conservative forces must also equal 0. Based on this conclusion, we can say that the mechanical energy of the system is conserved. In other words, the Ke initial plus the Pe initial at any given point in time, for that matter, is equal to Ke final plus Pe final. The best 2 points that can be used are the starting point where the mass is released from rest, because we have interest solving for the height that is related to that point. The other point has to be the top of the loop, because we want to make sure that the mass is going to negotiate that top turn without losing contact. Notice that the kinetic energy initial is 0 because the mass starts from rest. Therefore, this equation can be simplified as follows. The kinetic energy is 0. The potential energy initial is mghi, and this is the height that I am trying to solve for. The kinetic energy final is that one where the mass is located at the top of the turn, which equals to 1/2 mv final squared. Be careful, the speed at that point doesn't equal to 0, plus the mgh final, where the h final represents the diameter of the loop, or twice the radius. Notice also that the mass is a common factor, therefore it cancels out. This equation now can be simplified as follows. The gravity times the height initial equals 1/2 times the v final squared, which is the speed at the top of the loop, plus the gravity times the height final, which is equal to twice the radius of the loop. Since the h needs to be expressed only in terms of those quantities that are mentioned in the question, which is the radius r only, therefore I need to get rid of this v final. The v final is that speed when the mass is located at the top of the turn. In order to be able to evaluate that speed, you need to use the dynamics of Newton's laws for objects that move in circles. Notice that the forces acting on the mass when it is located at the top of the turn are the mg and the normal force. The weight mg acts straight down towards the center of the loop. The Fn also acts straight down towards the center of the loop. Remember that the normal force is the force of contact that is exerted by the loop on the mass. The system coordinate that we need to use for this motion is that one that will have the y-axis pointing straight down towards the center of the loop, and the x-axis is horizontal. Now let's apply Newton's second law to this system, where the sum of the forces equal the mass times the centripetal acceleration. The forces are the normal force is 1 and the mg is the other. They add up to the mass times the centripetal acceleration. Clearly the x component is not important at all. However, the y component will include the normal force and the mg, and both of them are positive because they point towards the center, equals mv squared over r. This is the speed at the top of the loop, and this is the one that we need in our equation to be able to solve for the height h. Since the question is asking for the minimum height where the object is released, therefore the normal force at that point needs to equal 0. That's the meaning of the object is barely negotiating the top turn. As a result, this y component is going to turn as 0 plus mg equals mv squared over r. Notice now that the mass is going to cancel out, and we can isolate the speed squared to equal g times r. Let's take this v squared and substitute it in the equation that we have obtained earlier from the conservation of energy. The equation now is going to have the following form: ghi equals 1/2. Instead of v final squared, we substitute that with g times r plus 2 times gr. Note that the gravity g is a common factor, therefore it cancels out. Therefore, the hi is going to equal 1/2 r plus 2r. The total is going to equal 2.5 r, and this is the minimum height that the mass can have so that it barely negotiates the top of that loop. If the height is lower than 2.5 r, the mass will lose contact before reaching the top of the turn.